Hello everyone, today we are going to see about theorem A. M be the closed linear subspace of the normed-linear space. So M be the closed linear subspace of the normed linear space if the norm of the coset, which means norm of the coset is x plus m, that is x plus m in the quotient space, that is quotient space is denoted by n by m, is defined by norm x plus m equal to infimum of norm of x plus m where m belongs to capital M. So then what we have to prove means if n by m are defined in the quotient space like this and m is the closed linear subspace of the norm linear space, we have to prove that the quotient space is a norm linear space, which is n by m is a norm linear space. Further, if n is a banach space means then we have to prove that n by m also a banach space. So quotient space is first we have to prove that quotient space is a non-linear space, then n is a banach space means we have to prove that n by m is a banach space. For part 1, what we have to prove means first we have to prove that n by m is a non-linear space. So the quotient space n by m is otherwise known as a linear space. So we have to prove the non-linear space. The quotient space itself is a linear space. So what remains here we to prove means n by m is a non-linear space. For that the non-linear space we have to define a 4 condition, which is norm x greater than or equal to 0 for all x, norm x equal to 0 for all x equal to 0, and norm x alpha norm of alpha x equal to modulus of alpha norm x, and then alpha norm x less than or equal to norm x norm y. So first we have to prove that norm x is always greater than 0. We know that the norm value is always greater than 0 for any norm space. Here the element n by m can be written, n by m is in the form of n x plus m. We have to prove that the n by m is a norm linear space. For that element is x plus m. We have to establish that norm, if we put the norm value means norm of x plus m also greater than or equal to 0. Now norm x plus m equal to what the given question is, infimum of norm of x plus m, m belongs to capital M. Since the norm is non-negative real numbers and norm of x plus m for all x belongs to m constitute a set of, for norm is non-negative, this also constitute the set of the non-negative numbers, non-negative real numbers, and it is bounded below. Infimum means it is bounded below, so hence the infimum exists, the condition is bounded and infimum exists and it is greater than or equal to 0. So norm x plus m is greater than or equal to 0. Since the non-negative real numbers, it is bounded and the infimum exists, so that is greater than or equal to 0. First condition we prove. Second, what we have to prove means norm x equal to 0 for all x belongs to 0. Okay, norm x equal to 0 implies x equal to 0 for any normed space. Next we have to prove based on our condition norm x plus m equal to 0, which is x plus m equal to 0. 0 is 0 of n by m. 0 of n by m is nothing but m. So let x plus m equal to, we have to take norm x plus m equal to 0 and x plus m equal to capital M, which is a 0 of n by m, if and only if condition. First we take x plus m equal to 0 of n by m, and then what we have to prove means x plus m equal to m. So we take x belongs to m, we shall show that x plus m equal to 0. Norm of x plus m equal to infimum of this value. Infimum x plus m can be taken as y, so infimum of norm y. M is the subspace, and if it is a subspace means it contains a 0 value, and norm we know is a 0, so infimum of norm y belongs to m equal to 0, so norm x plus m equal to 0 when norm x plus m equal to m. We take when x plus m equal to m, first we take x plus m equal to capital M, which is the 0 of n by m, then we have to prove that norm x plus m equal to 0. So we take x belongs to m, we shall show that x plus norm of x plus m equal to 0. So norm x plus m can be written as infimum of this value, and norm x plus m can be taken as y, and we know that subspace contains a 0. So infimum of norm y belongs to m equal to 0, norm x plus m equal to 0, x plus m equal to m. Converse part, we have to take that norm x plus m equal to 0, then we have to prove that x plus m equal to m, which is 0 of n by m. Consider now norm x plus m equal to 0 means infimum also 0. So if it is 0 means there exists a sequence mk in m. So yeah, norm of x plus mk tends to 0 as k tends to infinity, which is norm of x plus mk tends to 0, mk tends to minus x. So what we do means limit of mk is minus kx. So if we put a limit means limit of mk is minus x. Mk is the sequence in m which is the closest. So the limit point also converges to m. So it is a closed subspace. And here minus x belongs to m, additive inverse exists, so minus x belongs to m, therefore x belongs to m, which implies x belongs to also m. So x plus m also belongs to x plus m also equal to m because x belongs to m. Then x plus m equal to m means which is a 0 of n by m. This is prove the second condition. Next we have to prove the third condition, that is norm of alpha x equal to modulus of alpha norm x for any normed space. So alpha x is nothing but x plus m equal to infimum of norm of alpha x plus m, m belongs to m. Infimum of this is modulus of alpha norm of x plus m, m belongs to m. If we take alpha means infimum of x plus m, m belongs to m, which is nothing but norm of x plus m. We proved. Next, fourth condition, what we do means norm x plus y is less than or equal to norm x plus norm y for all non-linear space. Our x and y are x plus m, y plus m less than or equal to, we have to prove norm x plus m, norm y plus m. First consider this one. So by definition of addition of coefficients x plus m, so it is known as infimum of norm of x plus y plus m, m belongs to m. Then it is we have to m can be splitted into m1 and m2. So x plus m1 plus y plus m2, where m and m2 belongs to capital M. So that is less than or equal to